These questions are related to combinational circuits. So, what is the combinational circuit? So, you know that in that output will depend only on present input. Okay. So, now first question is write the output expression of half subtractor. So, in case of half subtractor, how many input will be there? Two input will be there. So, two inputs we are going to use here. So here in case of subtraction, we are getting the two output. One is called as the difference, another is called as the borrow. So for the difference, what is the expression? That all you need to remember. A XOR B. And for the borrow, expression is A dash B. Suppose they have asked here for half subtractor. Maybe they will ask you half adder also. Okay, half adder, full subtractor. For all these four, you need to remember the like here difference and borrow in case of subtractor, and in case of adder, sum and carry we need to remember. Now they're asking mention the truth table of 2 cross 1 multiplexer. So sometimes maybe they'll ask you define the multiplexer. Okay, so 2 cross 1. So multiplexer here, if you can write this one, you know that in general multiplexer, we are writing to the power n cross 1, where n is the, what is the n? N is the selection line. Selection line, number of selection line. How many selection lines will be there? So in this situation, it's written as to the power 1 cross 1. That means it has only one selection line. So when S will be 0, that output will be I naught, and when S will be 0, then output will be I naught. I naught is the one of the input. When S will be 1, then output will be another input, that is the I1. So this one, if you want to see in the form of truth table like this, also we can write this is I0, I1. So whenever selection line is 0, so if I0, then output is also 0. If I0 is 1, output is also 1. And this will be in the don't care, I1. Now when selection line is 1, two situation is there. Okay, I0 will be here, don't care. I1 will be 0, then output is 0. I1 is 1, then output is also 1. Now we have write the difference between sequential circuits and the combinational circuits. So this question is also very important. Many times they used to ask. Okay. So in case of, so you can write clearly combinational circuit and sequential circuit. So if it is 1 mass, write the two difference minimum. Okay. So that you'll get the complete mass. So combinational circuit is what? Its output depends on, you have to write clearly, outputs depend on present input only. Here outputs depend on present input as well as previous output or output state. Okay. Second point, combinational circuit doesn't have memory. Okay. So it doesn't have memory element. Whereas sequential circuit, it has Here also you can write has. It doesn't. It has memory element. Okay. So like this, these are the difference. Next, what they're asking. Next question is the truth table of the single bit comparator. Okay, single bit. Single bit comparator means when you are going to compare means we have two numbers. So single bit comparator means each number having one bit. Okay, that should be clear. So here one number is A and there is B. So each number having single bits. Okay, so this will come under the inputs. So with the help of single bits, how many combinations are possible? So two bits will get to the power 2 is 4, 0, 0, 0, 1, 1, 0, 1, 1. So here each number having only one bit, okay? A is separate number, B is separate number. And in the outputs, what are the possibilities? What is purpose of the comparator or magnitude comparator? Is going to compare the two numbers. Either A is smaller than B or A is equal to B, or next third condition A is greater than B. Only these three possibilities are there. So if you see the first combination, both are 0. That means A is equal to B. So another two conditions are not satisfied. So we'll write the 0. 0, 1. Which one is greater? B is greater. So A is smaller than B. So here we'll write 1. Remaining are 0. Next what we have? A is 1. A is 1, B is 0. So A is greater than B. So this condition is satisfied. Remaining are 0. Next, both are 1. So A is equal to B. Remaining are 0. Okay, this is the truth table of the single bit magnitude comparators. If they're asking 2-bit magnitude comparator means each number having two bits. So that we have to understand. Many times students do the mistakes in this. Okay. So what is the single bits and 2 bits magnitude comparator? Next, we are going to see the long questions. Okay. So here see that long question, same is what about 2-bit magnitude comparators. So 2 bits magnitude comparators means each number having 2 bits. So here I have done with the help of truth table. Okay. And we have another videos also in the playlist where it is done with the help of algorithm also, as well as tabulation like this also. So here if you see that if you have each number having 2 bits, so total how many bits will get? 2 plus 2, 4 bits. Okay. So with the help of 4 bits, we'll have how many combination? To the 4 to the power 4 is the 16 bits. So 16 bits means, okay, you can write the tabulation like this. If you have how computer is going to work, and when we have higher values of the inputs, then algorithm work nicely. One algorithm work for a small values also, but for higher values, you must have to use the algorithm. Otherwise, we can't write that much truth table. Okay. So now here, if you see that total 16 combinations are written here. Okay. So now again, three possibilities are there. A is equal to B, A less than B, A greater than B. So here you have to compare these two bits with these two bits. So both numbers, decimal will be 0, 0. That means A is equal to B. Remaining are the 0 here. Okay. Again here 0, 0, 0, 1. So A is a smaller than B. Remaining are 0. Next combination 0, 0, 1, 0 means 0, 1. That means A is less than B. Remaining are the 0. Again, if you see here 0 and 1, 0, 0, 1, 1, 0 and 3. So A is again a smaller than B. Okay, remaining are the 0. Next we have 0, 1, 0, 0. So A is greater than B. Next, what you have? 0, 1, 0, 1 means both are equal. Next again, 0, 1, 1, 0. Okay. So 0, 1, 1, 0, which one is smaller? A is smaller. Okay. A is smaller than B. Next, what we have? 0, 1, 1, 1. So again, A is smaller than B. Now 1, 0. Here A value is what? 1, 0, 0, 0. So which one is greater? This is 2. This is 0. So A is greater than, right? So 1, remaining are 0. 1, 0, 0, 1. Again, A is greater than B. Next, what we have? 1, 0, 1, 0 means A is equal to B. Remaining are 0. Next, 1, 0, 1, 1. So A is smaller than B. Next here, 1, 1, 0, 0. This is the what? 3. This one is 0. So A is greater than B. Now again, this situation also A is greater than B. Here also A is greater than B. Last one, A is equal to B. Okay, so this will be 1 here. This will be 0. So whenever, so therefore, situation will be there when A is equal to B, and like this we have to make the truth table. Next we have to make the K-map. So already you are knowing about much about the K-map. Okay. So here first one we'll take for the A equal to B. So whenever it is 1, that you have to write. So here it is A equal to B when combinations are here 0, 0, 0, 0. So that means mean term is what here? 0. Next again 0, 1, 0, 1. Mean term is what? 5. That combination you know, right? 0, 1, 0, 1. This 4 bits combination is this one is what? 5. Next again we have here. Okay, for this what we have? 1, 0, 1, 0. So 1, 0, 1, 0. So we'll get the this one. Okay. Next again one more. 1, 1, 1, 1. So 1, 1, 1, 1. Okay. So here that will be equal to 15. So here what you are saying that all are isolated only. Okay. There we are not able to write any combination is not possible. So finally here what we will write? F equal to A1 dash A0 dash B1 dash B0 dash plus second one A1 dash A0, and here we have B1 dash B0. Third one you have A1 A0 B1 B0, and fourth one A1 A0 dash B1 B0 dash. Now in this again what are the common terms are there, that all you can arrange, okay, and you make the proper function. So similarly, again, if you go for this another A greater than B or A smaller than B, so then you see. So here first we'll go for the A less than B. So when it is 1 here, when mean term is 1, this one, okay. Here again, this is the 2. Here, this is the 3. Next, this is what? 6. Next here, this one is 7. Next again, you have here, this is equal to 8, 3, 11. So, okay, 1, 2, 3, 6. Okay. So now here again, if you see that combination is possible. So this one we can make one quad here. For this, what value we'll get here? Row wise common is A1 dash and column wise common is B1. Okay, this is the common here. Now another combination, these two we can make the pair. Okay, so with this pair, what will be the value for this? What is the common? A1, A0. This both are dash. Column-wise, common is B0. Okay. Now one more is left. So for that, you can use the either isolate or better you can use the symmetricity for one also we can use here. So that is going to be here. Row-wise, what is the common in both? That is the A0 dash. Column-wise, B1, B0. So for this finally function is A1 dash B1 plus A0 dash B1 B0 plus A1 dash A0 dash B0. Okay. So this all, if you rearrange, you'll have some better combinations like some XOR gate, all this combination you'll get there. Okay. So similarly again here for A greater than B. So A greater than B when we have 1, 0, 1, 0, 0. So 0, 1, 0, 0 that is the 4. Again here 1, 0, 0, 0 means that is equal to how much? 8. So that combination you need to write. Okay. So here what we have? 8. Next what we have? This one is 9. Next what we have here? This is the 12. Next what we have? This is 8, 4, 1, 13. This one is how much? 14. Okay. So now these are the combination you are able to obtain. So now again, you have to make the combinations. So this 4 will make one quad. What is the value for this? Row wise, what is common? A1. Column wise common is B1 dash. Another combinations, this one will make as the pair. So for this pair, what we are going to get here? Common A0. Column wise B1, B0. Again, one more is left. For that, you can use the symmetricity. This one, this one. So finally, for this, what is the value? Row wise, we have A1, A0. Column wise common is B0 dash. Okay. So finally, here F equal to A0, B1, B0 plus A1, A0, B0 dash plus A1, B1 dash. So this one, they're asking design 2 bits magnitude comparator. So next you have to go for the logic diagram also. So before logic diagram, just to simplify the the function so that you can have simplest form of function and it will be easy to design. Otherwise, you can go for the algorithm also. Okay. So already separate video is provided for that. Okay. You can go through that. Next question is about design. This is also very important questions. Either they will ask you to design by using like here we have 4x1 multiplexer or sometimes maybe multiplexer along with OR gate also they used to ask. So now in this situation 16x1 multiplexers. Okay, so 16 cross means how many inputs would be there? 16. And 16 how we can write? To the power 4 cross 1. So here four selection lines are there. Okay, this four represent the selection line. And for the 4 cross 1, we can write to the power 2 cross 1. So here for each multiplexer, two selection lines are required. Okay. So on the basis of that, here we need to take four multiplexer at the first stage. Okay. So four multiplexers. So this will be the 4 cross 1 multiplexers. Again, 4 cross 1 multiplexers. So again, 4 cross 1. So at the first stage, we have to take 4 cross 1 multiplexer. Before that, you need to write about the selection lines. Okay. After that, you can start this design. So now in this, how many inputs are there? 4 inputs will be there to each multiplexer. So this inputs, okay, if you want, means you can write like in terms of A0, A1 like this, otherwise 0, 1, 2, 3. Similarly for this second multiplexer also, okay. And here you want means you can give the numbering when you are going to explain. With the help of this number, you can explain. So here inputs are 4, 5, 6, 7. So that means next four inputs. So here again, next four inputs. So that is 8, 9, 10, 11. Here again, four inputs. That is the 12, 13, 14, 15. So this is the multiplexer number 3. This is the multiplexer number 4. Now here, what we have to give? You have to give the selection lines. So same selection line will be used here for the, so each having selection line, how we represent? S0, S1, S0, S1, S0, S1, okay. Now it is important that which selection line will be connected here, okay. So this selection line in case of 4 cross 1 multiplexers, so suppose we are writing as A, B, C, D. So this LSB side multiplexer will be connected here for the first stage. Okay. So that is important here. So now here, if you take the value, this one, okay. So this all will be connected to S1. This one is the D, okay. This is connected to S1. So similarly, here also, so drawing is very important. You can use the scale properly. Next, we have another selection line, that is the C. Again, the same selection line. This is connected to S0. This one is connected again, S0. This is again connected to S0. So same C and D is connected to the primary stage selection lines. Next, you have one more multiplexer we have to use. Okay. So this is the again 4 cross 1 multiplexer. So this will be our fifth multiplexer, 4 cross 1 mux. So now here again we have two selection line. Okay. So that selection line again it is important. Okay. So that selection line again S0, S1. So finally here we have to connect with like we have connected here CD, here we have to connect with A and B. So that is important. Now output of previous stage, here this multiplexer output is going to be the input here. Again, this output is going to be the input. Again, this output, again, fourth multiplexer output is going to be the input here. And finally, this is our final output. So these are the inputs here, and here we are going to get the output. So here operation, if you see that, suppose this is the, suppose here I0, I1, I2, I3. Okay. So here you know about this selection line. So when we have S0, S0, S1, and what will be the, which multiplexer will give the output here. Okay. So when we have this combination S0, S1, that is 0, 0 means this multiplexer. First multiplexer output will be available here. Okay. So for the 0, 0 first multiplexer, for the 0, 1 second multiplexer output, 1, 0 third multiplexer, 1, 1 fourth multiplexer output will be available here. Okay, this is the combination for C and D. So again, we have combination of this A and B. So here again, when it is 0, 0, multiplexer 1 will be available to the multiplexer 5. 0, 1, again multiplexer 2, 1, 0, multiplexer 3, 1, 1, multiplexer 4. So this is the operation for the 4 cross 1 multiplexer of the primary level. Okay. So here two selection lines. For that you combination you know, right? 0, 0, this first one. 0, 1 like this. So finally for AB, and for this already separate video is also available. That lecture is available in detail. Okay. So that also you can refer. Next we'll have another questions. Okay. That we are going to discuss. So you can see the separate video for this also, that is recommended. Next question is about design a half adder and implement full adder using two half adders and OR gates. See, here they are telling us to design the first half adder. So first we'll go for the half adder. So in case of half adder, how many inputs are there? In half adder, two inputs are there. Okay. So that's why with the help of 2 bits, 4 combination as possible. And sum 0 plus 0, sum is 0, carry is also 0. 0 plus 1, sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. 1 plus 1, sum is 1, carry is 1. So this is only situation when we have sum as 1. So 1 plus 1, no, sum is 0, carry is 1. Okay. So that this situation we should be alert when we have 1 plus 1. So sum will be 0, carries the 1. Okay. So now if you see that the sum is looking just like a truth table of the XOR gate. So finally, for this, you can go for the K map also for the sum and carry separate, and you can find the expression. Okay. So for this also separate video is available. That also you can see in general. So now sum is what here? XOR gate. So we can write A XOR B. So this one we are getting by using the K map. And for the carry, only one time it is 1. So what is the combination? That combination is what? AB. So this sum and carry, you need to remember, even they will ask you objective questions. Now, so they're asking the design. So we have to go for the logic diagram. So logic diagram of this. So what are things are required here? One, XOR gate is required. The input of this XOR gate is what? Two inputs, A and B. So this output is going to give us sum. So that is A XOR B. Next, what we have for the carry, AND gate is required. And same wire connection we are going to take. Okay. Same A and B is given input here. So this is going to represent carry. Carry expression is AB. Now they're asking implement full adder using two half adder and OR gate. So already you are aware about this expression of the full adder. So that to implement this one with two half adder, you can have logic diagram with the help of block diagram, or we can go for with the help of gates also. Both are correct. So for this, what we required? Expression of sum and carry. So here, in case of full adder, we have three inputs. Okay, and third input is what? That is the output of the carry from the previous stage. Okay, so here we'll have two significant inputs, like A and B will be the significant inputs, and C in we are going to take the carry out from the previous addition. So for that expression is we have A XOR B XOR C in. So C in is what? This is the carry from the previous addition. And for the carry, what is the expression? Finally, we have for the carry, again you have A XOR B, okay, and this is the C in plus what is that? We have AB, okay. So like this two half adder, you can draw the logic diagram. Again, that output we are going to implement. So if you want means better we go for the block, logic diagram itself. So again here half adder you need to draw. Okay. So first here we are going to represent first what? A XOR B. So okay. Again we have another XOR gate is also required here. That XOR gate is going to be with C in. Okay. So finally for this your diagram is going to be like this. So you can use better representation with the help of pencil scale. So here inputs are A, B, C in. And here what is the output for this? First XOR gate A XOR B. And this one output is A XOR B. Again this is XOR with C in. Now we have another one. So for the carry, what is required here? AND gate is required. Okay. So this AND gate input is what? A and B. So finally, A and B is the output here. And finally, what we are saying that this is going to be OR gate with A XOR B and C in. So here you are saying that already you have A XOR B. So this we are going to utilize here again. So this is the another AND gate is required. Okay. Since this is here product. A XOR B is product with C in. So this C in is the another input. So this part you got. Now this AB. Okay. This AB is being added with previous first term. So that's why what we required here, OR gate is required. This one is going to give us carry. This one is expression for sum. So here what we have at this stage, AB. Okay. And this is what? A XOR B, and it is AND with C in, and this is the carry expression. So here we have A XOR B, C in plus AB. Okay. So like this we can implement. So here what you'll see that this one is the one half header. Half header 1. Similarly, we have another half header. Okay. This one is the another half header. So this one is our half header 2. So like this, we are able to implement by using two half header and OR gate. So next we have, this may be lengthy video, but it is very important for the examination point of view. These questions are going to come directly. Okay. So next we have discuss in detail about decoders. So decoders, here size is not given, but sometimes maximum time size will be given. Which size of decoder you have to design. So what is the decoder? So decoder, again, it is the combinational circuits. So where you see that when we have n number of the inputs, then we'll have maximum how many outputs? We have to the power n outputs. So maybe sometimes all outputs are not used, but maximum outputs is to the power n in case of decoder. Okay. So now this decoder size is not given, so we can take one of the examples. Suppose you want, you can design 3 cross 8 decoders. If you want, you can design 2 cross 4 decoders. Okay. So suppose here we are taking the example 2 cross 4 decoders. From our side, we have taken example here. So 2 cross 4 decoders means how many inputs will be there? 2 inputs. Okay. And 4 outputs. So for that, truth table is required. So in the truth table, first what we have here, inputs. And this side again, outputs. So this tabulation should be done properly. So inputs you are taking here, suppose we are taking X, Y, or you can take A and B, and outputs how many will get? 4. Okay, so decoder, so D0, D1, D2, D3. So this 4 output will get here. So for that here, how many combinations are possible with the help of two inputs? 4. So 0, 0, 0, 1, 1, 0, 1, 1. So now when input is 0, 0, D0 will be 1. Remaining outputs are 0. Again when 0, 1, so here you can see the suffix D1. 0, 1 is 1. So this is the 1, remaining are the 0. Next 1, 0 is what? 2. D2 is 1. Remaining are the 0. 1, 1 is 3. So D3 is 1. Remaining are the 0. So here what you are seeing that diagonal elements are 1. Okay. Remaining are the 0. So for this again you can go for the logic diagram. Okay. So in case of logic diagram, you have to design. So for this, how many inputs are there? 2 inputs are there. And these inputs are coming with complement also. So we can use here wire like this. And again, this one with complements. So inverter is required. So suppose this is the X. Then another will take as the Y. For that again, we are going to use the inverter. Okay. So here AND gate is required to design this. How many outputs are there? 4. So 4 AND gates are required. Okay. So each AND gate will give one output. So suppose this one we are taking for D0, this is for the D1, this is for D2, and this is the D3. Since it is the AND gate, so when all input will be high, then only output will be high. So here D0 is going to be the output. So what is combination? 0, 0. So 0 means X is 0, Y is 0. So that inverted output will be connected here. Okay. 0, 0 means complement. Next, what we have? 0, 1. So X is 0. So X inverted 1. Okay. And Y is 1. So this will be connected. So next, always X and Y you can keep high. On the basis of that, you can draw here. That also possible. Next, X is 1. So non-inverted. Y is 0. So inverted. Last is each is 1. Okay. So X also 1. Y is also 1. So like this, you have to give the connection. So this is going to be here. So from where we are taking the wire, you make the proper dot. It will show that we are taking the input from there. Okay. Apart from this, for decoder also separate videos are available. Okay. And sometimes maybe in question they will ask you design the decoder with enable inputs. So that enable inputs means one more enable inputs will come and that will be designed with the help of NAND gates. Like here we have designing with the help of AND gates. So both possibilities are there. So okay, and you can have sometimes they will ask 3x8 decoder also. Okay. So these are the discussion from here from the combinational circuits. Okay. So go through this. Okay. Watch it again and again and like, subscribe. Thank you. Thank you very much.